Hello and welcome to the session. In today's session, we'll be discussing about block 3 of MCS-12, which is about the central processing unit. Now, you may be wondering that we have already done, the slides are not moving, please check. We have already done a session on, so this basically covers MCS block 12, that is what I have been saying, that is the reference material. Okay, and what we'll be doing in this, why we are taking up block 3 after block 4. Technically, block 3 is about the central processing unit, and central processing unit is responsible for execution of instructions primarily, and those instructions are machine instructions, right? So when we learned about the assembly language programming and the microprocessor, what we technically discussed was one of the implementation or one of the examples of a machine which happens to be 8086 microprocessor, and the assembly instructions technically are equivalent to machine instructions only. So that gave us an idea of how machine instructions for a machine for 8086 look like. Therefore, now you will be finding that whatever we will be covering in this block will be somewhat easier for you to understand. Okay, number 2, what I must emphasize for you is that you must see all the videos we have done so far. Right? They were actually recorded as live videos, but technically they are just the broadcast videos. And what you can do at your end, you can stop in between, like you can stop this particular video in between, look into your block, look into the slides, and go on. Go on learning, solving problems. And if you are stuck at any point of time, please do not hesitate to ask questions. It's very, very important that you ask questions, and you already know where exactly you can ask questions, right? So let us begin what we have to do today, right? So today's presentation will be focusing on the instruction set of a computer. So we'll be talking about instruction set in general, and one instruction set we have already discussed about is 8086. But that and this will try to complete your information about the instruction sets. Then we will be talking about micro operations. Now what happens, you have a given instruction set, okay? Now if we extrapolate it, you have C program, right? And C program is a higher level language program. So any instruction of C, first, if it is to be executed, converted into machine level instruction. But machine level instructions are somewhat equivalent to assembly level instructions. So technically speaking, your C program will be converted to equivalent machine or assembly equivalent program. Just leave aside the assembler directives and so on and so forth. But technically one assembly instruction is equal to one machine instruction, right? So keeping that particular constraint condition into mind, what we are trying to say, so these instructions, then a bigger program to smaller instructions of machine level. However, to execute this machine instruction, you once again require even smaller level of instruction or steps. Okay, so this is what we would like to discuss today in the form of, these are called micro operations. And micro operations are very close to computer organization of that particular machine. Okay, so basically organization comes into that existence at that point of time. So somewhere very close to the hardware, and we would like to discuss some of the circuit, very close circuit related to that kind of a situation. And finally, we will talk about ALU organization, like how ALU will be executing those instructions. What I would like to emphasize over here is that ALU execute instructions in a step-by-step manner. And those steps are to be followed in a very, very sequential manner, just like your C program when you write, right? It's followed in a very sequential manner. From first instruction, we move to the second one, unless explicitly you have given a looping instruction. So similarly, in machine level also, we follow that kind of a sequence. ALU follow a typical sequence of instruction, and if there is a change in the sequence, that also is to be told. So that is where the control unit of a machine comes in. Alright, so this is how the whole organization of this particular block 3 is. Okay, so it starts from like what is an instruction set, moves on to the micro operations, micro operation then to ALU, ALU to control unit operations, and then finally we have discussed about a reduced instruction set architecture in this particular block, which we may not be discussing in this particular session. Okay, moving on to the instruction set. So what do we mean by an instruction set? Technically speaking, simply a set of all the instructions which processor can execute, right? So every processor is supposed to execute a specific set of instructions. And if you remember your 8086 microprocessor, several of those instructions we have discussed. I'll give you some example once again here of those instructions. Okay, but there are a number of instructions which are to be executed by the processor. Okay, but what is an instruction? Like what are the basic components of an instruction is? Well, instruction consists of three basic things. The first one is operation code, right? The second one is addressing modes, and the third one is operands. Now, operation code basically tells the CPU, in fact it will be telling the control unit as well as ALU what operation is to be performed. For example, addition is to be performed, or subtraction is to be performed, or multiplication is to be performed, or XOR is to be performed, what operation is to be performed. So there is a typical operation code, and remember these operations, when we use assembly, they are mnemonics like add, XOR, etc. But technically, a machine instruction will always be in bits and bytes. So how the computer will recognize this is an instruction? By the context. When control unit is executing that particular instruction, right, it knows which one is instruction and which one is data. So it is the context of execution of instruction where control unit controls the whole operation very, very well in the central processing unit. So operation code is also binary, right? Just like your ASCII is also binary, right? Okay, then addressing modes. Now we discussed 8086 addressing modes, if you remember. Addressing modes basically tell us that how and where operand can be found. So how an operand can be found is addressing mode, and operands, where exactly are the operand, the address of the operand is where it is going to be found. How and where. Okay, so this is how. So basically an instruction will consist of what operation to be performed and what data on which that particular operation is to be performed. And remember one thing, all the things will be like instructions will be stored in the, it's a von Neumann machine architecture in general, right? Although even if even you use that virtual machine, even then the instruction has to be in the main memory before it executes, right? So keeping all those things in mind, what we really know that instruction is one of the simplest of the things. Operation code, addressing mode, operands, they will be stored in the memory, von Neumann architecture, and even the operands are going to be stored into the memory or registers, right? Registers are another, because registers are the temporary locations within the CPU which basically help process the information or data in a particular sense, even interpretation of instruction, so many tasks they do. All right. Now, a very important statement which has been made in this particular slide is the number of operands in an instruction. You know, the importance of number of operands in an instruction is very, very high. Why? Because the program size is very much dependent on the number of operands within an instruction. I have shown you an example. Suppose I'm using an instruction set which allows me to use 3 memory operand like the first instruction shown over here. So what I can do in this particular case, what I'm saying, my instruction is add Z X comma Y, where Z is a memory location, X is a memory location, Y is a memory location. And you know, the larger is my memory, larger is the number of bits required of the address, right? So address of Z will be large, X will be large, and Y will be large. So overall this instruction is going to be very, very large, but only one instruction is serving the purpose where Z is we are adding x plus y and putting the result into z. So only one instruction is required. This is the condition for a machine which allows us to have 3 such operands in a particular instruction. However, when we remember 8086, it allowed only 2, and even 2, and one of the operand had to be memory operand, right? So that can be somewhat can be equated to these 3 instructions. So considering a machine where all the operations are performed in the accumulator, so that's why we are naming it AX. So all the operations are performed in accumulator machines. Then how this particular machine, the program will be written? Same program. Z gets x plus y, right? How we are going to perform? The program is to be written like this now. Load x, right? So x will be loaded to accumulator. Then add y into the accumulator, right? So x was already into the accumulator. Now y has been added to it. Okay. So we get x plus y in the accumulator register as a result of this, and then store z. So basically the third operation is going to take ax, that is the sum of x plus y to z. So you can see, if the number of operands which are allowed in a particular instruction and their type, right, if they are not, or not all are memory operands which are allowed, I require 3 instructions, 3 machine instructions. Where in this particular machine I only require 1 machine instruction. So this is the essence. Like, many machines will have different instruction sets. 8086 has a typical instruction set, but that instruction set is only belonging to x86 family, right? And the newer processors have entirely different sets of instruction these days. Just for backward compatibility, they still have kept the 8086 instruction set available within those instructions, but they have newer instruction sets available, RISC-oriented instruction set available, where the number of operands may be less, right? But they are doing specific tasks in a particular sense. Anyhow, our concern is that different machines, different kinds of instruction sets. The size of the program does depend on the number of operands which are there within a instruction. So this is what is the explanation of this particular part. Now, what are the issues related to instruction sets? The very first issue is instruction formats and instruction lengths. So what happens when we are dealing with the different microprocessors, the instruction lengths can be different. Okay. In fact, when I was talking about 8086, I made a specific statement that an instruction of 8086 can vary from 8 bits, that is 1 byte, to 6 bytes. So there may be different kinds of operand code. Even the length of operation codes are sometimes different in those machines, right? So those machines will have different kinds of operation code, different number of operands, okay, and different addressing modes, making the instruction length very, very different, right? So those basically come under instruction formats. So there can be multiple instruction format where you will have, suppose you have one memory and one processor operand. Okay, so that can be one typical kind of instruction format. There can be a second instruction format where only one operand is specified. So that is a different instruction format. So there can be different instruction format, and which will be of different instruction length. Well, remember one particular thing, length of instruction is in bits, and bits are at a premium in any processor, right? So instruction length designer have to ensure that all the operations which are important for a machine are part of machine instruction set. Otherwise, machine will require longer time to execute a program. Okay, this concept I'll explain a little bit later also. Now, how many number of operands? Okay, this I have already taken. There can be number of operands, 1, 2, 3, and they determine the size of the program. So we need to determine. If I have 3 operands, as I shown in the last example, what is the problem with that? The problem with that kind of a situation is your instruction length is going to be very, very long. and you don't want to compromise on instruction length. Suppose a simple instruction can be clear, right? So clear a register. Now that instruction doesn't require much of a space, right? It has to be very, very long. So there has to be a compromise, right? There has to be a compromise when we are designing the instruction set. Then the third thing is different data types supported by machine, that is numbers, character sets and logical bits. So data types in a machine can be numbers, and in numbers we have choice. We can represent fixed point numbers. The 8086 have only fixed point numbers. Alright, so if I want to perform floating point addition, I required a coprocessor in that particular machine. Alright, a coprocessor was designed for the purpose of floating point addition, so that any instruction which required floating point addition was passed on to the coprocessor if it exists. Otherwise, there will be a big sequence of instruction which are to be executed, like mantissa need to be checked for, exponent need to be checked, then the denormalization is to be performed, then the addition or subtraction is to be performed, then normalization once again is to be performed. So there is a sequence which are to be performed. Had this been implemented with the help of hardware in the coprocessor, then the overall execution of instruction become faster. So if an instruction can be implemented by the hardware, it is always faster. If it is to be simulated with the help of other instructions of the machine, obviously it is going to be slower. So that is how the instruction set designer have to debate whether I would like to include floating point instruction within the processor or not, right? How many, but the more instruction you include, the bigger is your instruction set. The bigger is your instruction set, the control unit for that particular unit is going to be, or control unit and a arithmetic logic unit, or all those operations are going to be more and more complex. So all these trade-offs are done by instruction set designers, so we rely on them. They are very competent people, and let's believe that they are doing their job properly. All right. Then different types are supported, right? So different types of data I already said. Okay, character set we have already studied. The very first type of character set, ASCII or Unicode, UTF-8 or UTF-16, right? So what kind of character set this particular machine is utilizing? In numbers we also have BCD, which we discussed last time, binary coded decimals, whether addition is to be performed using BCD or not. 8086 allows us to perform BCD based additions, right? So this is how the numbers comes into play. And then logical is zeros and ones only, so the operations related to logical bits. Now different types of instruction, most of these instructions you will find these are from 8086 only, right? So they can be data transfer instructions which simply moves data among various registers or memory locations, right? Push pop from the stack. Translation is a different kind of instruction which translate the data into from a given set to another. Then exchange, basically exchanging two pieces of, two values stored in two different locations, and only one of them can be memory, like that. Okay, so data transfer instructions are there. Then the data processing, where arithmetic instructions, we add, ADC, increment, multiplication, ASCII adjust after addition. So lots of instructions, which all these instructions are coming from 8086. But there can be many more such instructions. There is no limit on the type of instructions which an instruction designer has to do. All right. Then comes the DAA, and DAA is after AAA. So there is a slight logical is basically not, and, or, XOR, shift left, shift right, test. Shift left, shift right are very, very important, so we will discuss about them. Test we had explained in the 8086, so you will know about it. Program control is very important, okay? So I'll be discussing about call and return a little bit later. Jump we have already seen, loop we have already seen in our sessions on assembly language programming, and then there can be miscellaneous instructions like 8086 has the string related instructions and processing control related instructions, which basically are utilized for special purpose. So in general, a processor will have all I mean not all, but many of these instructions as per the suitability of the design of that particular processor, right? And the decision is taken by the instruction designers. Now, as I was talking about shift instruction. Now, shift instruction is very important. There are three kinds of shift instruction. First is called logical shift, second is called arithmetic shift, and the third is called rotation with shift. So it is not shift, it is rotation based shift. All right. So if I say shift right, all right, so you can see how the things are moving. So logical shift right, all these three types of instruction, that is logical, arithmetic and rotation, they differ only how this bit is going to enter here. If it is a logical shift right, okay, this bit will be moved here, this like that, these movements of bit will be there, and this bit will be going out. All right, this just going out and going nowhere. And 0 will be entering over here. This is a logical shift. All right, so this is the shift right, and in shift left, 0 will be entering over here and everything else will be moving. All right, this bit will be moving out, bit by bit movement out there. So this is a simple shift instruction. And if you remember, we did shift by 4. So 1, 2, 3, 4. 4 times this particular shift operation like this will be performed. All right. Now, when we talk about arithmetic shift, in arithmetic shift, sign is to be, this is actually representing the sign then, right? So this is maintained. So whatever is the sign, it is going to be maintained as it is. 0 will be added here, but the sign will be maintained as it is. So basically, you are not moving sign bit, you are just moving the bits otherwise. Okay. So you are just preserving the sign bit. When it is shift left, when rotation, that means when this bit is falling off, so it will go back to the highest. So 0 will not be entering here. This bit will be going back to this particular location. So this is a rotation. All right, and we actually perform the rotation. All right, so 0 will not be entering here, but this particular bit will be coming back and staying over there. So this is the way shift operation works. And shift operation is very simple to implement with the help of shift registers, which you have studied in the block 1, right? There are left shift and right shift registers which allow shifting of content. Now this is a very important instruction for us, subroutine call. And this is a very typical example of subroutine call and how it is working. Okay, so what we have, this is our main program. Okay, so there are a subroutine called named X, all right, and subroutine is at location 200, 201, 202, right? So this is basically performing some operations, and thereafter subroutine at some point of time has to return to the main program. All right. So how exactly this sequence goes on? Okay. So whenever there is a subroutine call, so this is the flow of control. So program starts executing. It went on to 100, then 101. As soon as the 101 instruction is executed, which is a call. So what exactly is going to happen? All the parameters, right? You actually pass parameter, and you can study this particular concept in unit 4 of assembly language programming also, block 4, where the parameters will be passed. We have not shown the parameter passing in this particular case. We are just showing the subroutine call and subroutine return, how exactly it is going to take place. But technically, there will be a call to a subroutine and there will be parameter which will be passed on to the stack. Okay, that example you can refer to block 4, unit 4, right? Okay, so it will happen, the parameters will be passed on through the stack, all right? Then the call, whenever you make a call, a return address is to be stored, all right? And that return address is to be stored. Now, where exactly the program will be returning after passing all the data? To the next instruction. The program counter should, like how the execution is, 101 will be executed followed by 200, which happens to be the subroutine, 200, 201, 202, 200 up to 300. This subroutine will be executed. When it says return, all the data values will be passed to this particular statement, and program control will come to the next statement after the subroutine. Okay, so that is the return. So return is to the next, that is 102nd location. You can see the 102nd location has been put onto the stack as the return value, and stack pointer, which is not visible unfortunately, SP is pointing to that particular location. Alright, so this is how a subroutine call is going to be executed. Okay, so this subroutine executes, function executes completely, then the control returns, alright, then 102nd is executed, 103rd instruction is executed, and at 103, once again there is a call. So then the flow of control goes like this, executes, and then 104th instruction will be executed once the subroutine is executed next. How we are storing the return address? Onto the stack, onto top of the stack. As soon as the return statement is encountered, this next instruction to be executed is restored into the PC, alright, and all the data is passed to that is this particular instruction, all the data is returned to this particular instruction, and control PC gets this particular value. So next instruction to be executed is going to be this, that is 104 in this particular case, and in 102 in the other case. So that is how exactly our whole sequence of instruction execution, okay, program control takes place whenever there is a subroutine call. And this concept is very, very important for you to understand the concept of call by value in C. Okay, call by value, etc. Okay, the stack is being utilized. So all parameters will be stored above it, onto the stack. Onto the stack, all the parameters will be stored, and the return address, and those parameters, when you play up with those parameters, the original values doesn't get affected. And that is where it is call by value. So you will learn about call by value in C programming, in C++ programming. It's all based on this particular concept which you are learning in computer organization course, right? And you should be clear about this particular concept because this is very, very important. One important thing which has been hidden over there is SP gets SP minus 1 because the stack grows in reverse order. Alright, so stack is growing from 505 to 504, 503, 502. So it will grow up and it will come down. So when you are pushing something, when you are putting something into the stack, you will be decrementing the stack pointer. And when we are taking out something, you take it out and then decrement the stack pointer. That is how stack works. You will be learning about stack in more details when you go to, when PGDCA students go to PGDCA second semester, MCS student goes to the second semester, and BCS students when you learn the data structure course. Alright, so remember this concept, it will be useful at that point of time. Alright, the second thing which I would like to take up with you is the addressing schemes. We have done addressing schemes for 8086 processor. Here we are consolidating all those addressing schemes with the help of an example or a diagram in that sense. So this is my program, alright. It is in the main memory. Okay, so the first addressing mode, so this is addressing mode. This is the instruction, that is operation code, and this is the operand. Alright, so this is the operand. So when I say within, now this is my instruction. So this instruction I'll be executing, I'll be taking it to instruction register. But we are showing just the instruction for the sake of where exactly the data will be residing. Okay, so when this instruction, okay, when that is immediate instruction mode is used, this actually 7 becomes the operand value. Immediate means operand is residing within the instruction. So when this load statement is to be executed, okay, obviously this instruction will be fetched into instruction register, it will be decoded, and when we know that this is the operand that is addressing mode happens to be immediate, that means whatever value 07 or whatever value is in the operand mode, operands of the machine, that will be directly transferred to the wherever the first operand. In this particular case, it should be AC. So this value will be transferred to AC. So you have initialized that particular value of AC by 07. So this particular instruction. So if it is immediate operand is there, it's very easy to execute the instruction. So why not all immediate operands? Well, immediate operands are very useful when you are initializing a value, but you change values all the time. Alright, and when you change values, you have to bring those values from some location. So initialization, some constants, okay, in those cases you use immediate operands. Very useful for that because they are directly available in the instruction itself. So you don't need to fetch the operand at all, right? Instruction fetch itself is going to bring the operand. The second addressing mode, which is the most important for us, because most of the time instructions are going to be, that is, the operand is going to be reside in the memory location. Okay, so this is that case. Load D happens to be direct addressing mode, and operand address is 500. So location 500 contains my operand. So when this instruction is fetched into the instruction register, the operation, that is addressing mode, will be direct. So this value, that means that in the next step, this 500, that is location content of 500 is going to be brought into the CPU. Only then processing can take place as far as this instruction is concerned. However, this is one of the necessity because most of the time in von Neumann architecture, we are getting the data from the memory. Cache is going to definitely help in enhancing the speed of this particular operation, but cache is not going to do anything else other than that, right? So cache will definitely enhance the speed, overall speed of execution of this particular instruction. Why? Because if I am bringing data from 500 location, then it is taking, the memory is, as we said, around 50 times slower. So it may take slightly more time. But if we use cache and the data is available in cache, the speed of the cache and processor are almost identical, although cache is a bit slower. So we will be running almost at the speed of the processor. So this is why it is going to enhance the speed of overall execution. So cache is just going to enhance the speed, but addressing mode is this way you interpret the addressing mode. Now this is a very, third is a very interesting, it is indirect. That is what is being represented. Indirect 500. So the location 500 stores the address of the operand. Okay, so indirect means that this location stores address of the operand. That means first I'll be bringing the address of the operand into the main memory, and then I'll be able to bring the operand. So this indirect mode of addressing, memory addressing, is somewhat very expensive, and nowadays it is not being utilized in the latest of processor. This is there for the historical purposes. However, instead of indirect location, that is memory location, registers can be used, indirect mode of registers, right? So that is what you can see is somewhat visible over here, where instruction is having a register which basically shows the address of the operand. Okay, so then the register, that is, this is also indirect. So that is, register has the address of operand which is then fetched, and the instruction, the advantage of this kind of situation, you remember we used BX and SI, right? That kind of addressing modes in assembly. Okay, so this is very important. Why this is very important? Because the register actually hasten up this indirect mode in a much better way, because register is already with the instruction. Okay, it is already in the CPU, so it will hasten up the operation of fetching the operand. Alright, and this is the final one where some displacement is also added in the register value. Once again, that displacement is part of the instruction. So this kind of an addressing mode is mostly utilized when you are dealing with arrays. Okay, sometimes you use auto indexing, then you don't require this offset, but this offset is that this is the first location of array, and this A represents that is your index, that is the loop invariant. First location, I can be 1, 2, that's how you address an index array, right? Array is being stored, okay, somewhere, which will be pointed to by register R, the base location, and within the array, which offset, which element you are trying to refer to, 5th, 6th, that will be in the offset, and both are added to form the actual address within the memory. So addressing modes are very important, and these are the 4 or 5 addressing modes which are very common, and most of the time, barring the indirect one, these 4 are picked up for machine instructions, and this is the case for 8086 microprocessor also. You will find that they are existing over there. All right. So this is what we have talked about as far as what we have talked about the instruction set. But instruction set cannot execute without the registers and the ALU structure, right? So I just want to bring once again the context of ALU structure. The units of ALU like bus interface unit and execution units of 8086. All right. In fact, that is the whole microprocessor in a particular set. Let's not simply put it to ALU. Okay. So we had two units of the microprocessor, bus interface unit and execution unit. So take it as basically ALU structure will do a little bit later, but a microprocessor technically consists of some structure, right? Some units which can execute in parallel like bus interface unit and execution unit of 8086. And then the registers which are responsible. If you remember 8086 microprocessor, there were segment registers, there were AX, BX, CX, DX, general purpose registers, right? There were special purpose registers like segment registers, there were pointer registers, there were stack pointer register, there was instruction pointer register which is pointing to the instruction. Okay, so all that registers were there. And there were flags registers which are also a sort of sometimes special purpose register. Each flag register is one. Each flag register consists of several bits. So each flag is only one bit. All right, that is the common convention in most of the processors, and through this what we are basically knowing the basic structure, okay, basic structure of the CPU which is there. Now we know what instruction set should be required, what addressing modes are required, right? What are the kinds of how the operands, that means how the addressing modes basically tell us how the operands are going to be addressed. All right, so this is how we basically know about various things as far as microprocessors are concerned and the processor is concerned. But how exactly these operations will be performed? All right, now that is one of the most important situation for us. Think in terms of any instruction you take, okay, right? Suppose we assume an instruction, let's say this instruction, execution of increment A and skip the next instruction of the result if the result is 0. Okay, now this instruction we are wanting to execute. All right, that is add and skip. All right, add 1 into a particular register. If it comes out to be 0, the result comes out to be 0, then skip that means the value stored may be negative value in that particular register where the value is to be added. Now think in this particular instruction in a very simple manner. This instruction will be residing where? In the memory. It cannot reside anywhere else. All right. Now the first operation. So if I want to execute an instruction, I'll be requiring step-by-step execution of the operations which will execute an instruction. Now this is very important for you to learn. All right. The first thing you need to do, please remember this, you got to bring the instruction from the main memory to the processor register, okay, which we normally call instruction register. All right. So when we want to bring instruction to instruction register, only then it can be decoded and executed. All right. So this is the first. Just don't concentrate on this part. Just concentrate on this particular area. So the first thing is I need to bring the instruction into memory. All right. So how do I do that? Where exactly is the address of the next instruction resides? The program counter register. All right. So this program counter register contains the address of next instruction to be executed. Now I transfer the program counter to memory address register, which is interfaced to what? Which is interfaced to memory bus. All right, the processor to memory bus. So it is interfaced to processor to memory bus. Technically, memory address register is AR stands for address. That means this register applies its content onto the bus for the memory. Alright, and they can be latches also, which will store from the bus. The data can be stored by the memory unit. That is a secondary kind of a statement, right? So we are not going to go into that domain. We are simply saying that the first statement is PC is transferred to address register. Then the control unit will be asked that the next sequence I want, whatever location is addressed by MAR register. That means address register will be putting this information onto the bus. Okay, the address unit of memory will be latching on, taking that particular information from the address bus. Okay, at that point of time will get loaded with the address, the content of address bus. All right, who will control that? The control unit, okay, by issuing appropriate control signals for that. However, what micro operation is going to be performed at that point of time? The data register, right? So whatever is pointed to by MAR, memory address register, okay, so that content will be put onto the data bus, and data bus content will be cached by the DR register. So this is the second micro operation. Okay, what does it integrate? That whatever location has been pointed to by memory address register, that location, that means PC, right? PC was the address of the memory location, right, where the next instruction is residing. That instruction now, right, comes to DR register. All right, so DR gets that particular information. Since I have already done up with this PC, in parallel, I don't need this PC anymore. It is to be incremented to the next instruction. So assuming that the next instruction is residing in the next memory location, so I simply increment PC. This is a very simple machine, okay? Not complicated, so that you can understand how machine actually works. Alright, so PC gets incremented to the next instruction, because this instruction have not now been fetched to DR register. It will be fetched to DR register. Address has already been put, so I don't need to worry about it. So increment the PC parallelly, right? So these two operations can be performed in parallel. Alright, so only one, during the same time these two operations will be performed. Okay, and then finally instruction register gets the data register. So this value is transferred to instruction register, which basically is related with the control unit. So for interpreting it, we will simply transfer it into instruction register, where the operations can be performed. Alright, so this is how the whole sequence of instruction fetch works. This is for a typical machine. It's not that it will be required for all the machines. This is not going to happen for all the machines. Every machine will have different set of micro operations. But with this simple set of micro operation, what we are trying to tell you, that even a machine instruction will require several steps at different point of time. Alright, and this is actually comes under the category of complex instruction set computers, right? So in any case, all the machines will have a sequence of steps. So this is how the machine instruction is fetched. All right, so now that instruction is in instruction register. What is the next step of execution? The next step will be, let's decode this particular instruction, and which will be done by the control unit. How the decoding is going to take place? The operation code, right? Operation code will be checked, and operation code is actually used to branch to a control memory location where the microprogram of that particular instruction resides. So every instruction has its own microprogram, and that microprogram consists of sequence of micro instructions. Each micro instruction deals with one time, one time of micro operation. So these two will be dealt with together. This will be dealt with one micro instruction. This will be second. This will be third, like that. But these are for fetching the instruction, right? Here what we are referring to, decoding the instruction, right? So decoding, basically decoding is simply a jump. Decoding simply causes a jump to the related microprogram, and we will see the execution oriented microprogram very shortly. Alright, then the next thing which need to be done is the operand. Okay, when you have decoded, you also decoded the addressing mode. Alright, so addressing modes tells us either it is a direct address, right? It can be immediate also, but that has been ignored in this particular case. So what we are referring to, only two addressing modes, direct addressing mode or indirect addressing mode. Suppose it is a direct addressing mode, then in the indirect register, whatever is the address portion of the instruction, alright? Sorry, not indirect register, this is instruction register. So in the instruction register, whatever is the address portion of the instruction, that contains address of the operand, if it is a direct operand, right? So both these registers are containing the same value because DR and IR contains the same value so far, alright? So basically address portion of instruction register contains the operand. However, it is an indirect address, then the one which we shown, right? That is the memory location. So what will happen? That address will be passed on to MAR and the instruction, that is the data. This time we are not fetching the instruction. This is the address of the operand, right? So the address of operand is in the MAR register, and that MAR register is now being fetched into DR. That means whatever now we are getting in the address, IR address portion will be the address of the operand. Alright, so we are reading it once, okay. Here we have the address in the instruction register itself, but here we have to bring it from the memory because it is an indirect address. So the address of the operand is within the memory. So that memory location is going to be fetched with these two instructions. That is, address of that memory location will be passed on, and then it will be read. And what have you read? You have read the address of the data which is in the memory. Okay, so now indirect address technically has been converted into a direct address. So instruction address now, after execution of indirect address, will contain the address of the operand, effective address of the operand, where exactly the operand is residing in the memory. That's all. So here we are assuming that operands are in the memory. In direct case, directly that address is available to us. In indirect case, once again we do the fetching to get the address of the operand in IR. So now instruction register contains what? Address of the operand within the memory, right? If it is direct, it already contains. In the indirect, we will be fetching the operand address once, alright? So that is how the indirect address is going to work, alright. Now comes the most important part. Okay, execution of increment A and skip the next instruction if, right, result is 0, not off. Okay, now how this particular situation is proceeding. So now what does my instruction register address part contains? The address of the operand, right? So that address we are passing on and getting the data into the data register, right? So you apply that, you give that address to MAR and issue the memory read operand operation. Control unit will do that, but micro operation is, this is the reading micro operation. That is, whatever is in the memory location, that was the operand location, so that is going to be brought into DR register. Alright. Increment A. So A has been brought. Where exactly was the A? A, assuming that it was an indirect or direct operand, it does not matter now in this particular case, because had it been an indirect operand, it has already been converted to a direct operand. If it is direct operand, then no step is needed. Alright. So now A is brought into the memory as a result of these two micro operations. Once A is in the memory, right, what is it to be done? Increment A. Now incrementing it in the accumulator register, here we are assuming R1 is the accumulator register. Alright, so then we are taking that is the value of A into R1 register, increment the R1 register, and DR gets the R1 register, right? DR gets the data register gets R1 register in addition to this particular thing. MAR gets PC, alright. MAR is given the value of PC, and that particular value is stored back into A, right? Incremented value. Now this is writing. MAR gets the PC value. Now DR is written back to MAR register. So you have incremented the value of A, right? So incrementation of value of A will be completed after we have written that particular value into the memory location, right? And that memory location was already there. Okay, right? This PC, actually this MAR to DR is good enough. This step may not be needed in this particular case, alright, because we are not reading the next instruction. Okay, now comes the most important stuff. If R1 equals 0, so just forget this particular line. So DR gets R1. When DR gets R1, okay, and it is basically what you are doing, you are writing it to the memory location whichever was belonging to A, right? So you have written the data, you have incremented the location A, alright. Now if R1 equals to 0, right, what we have to do? Then PC is incremented by 1. What is the increment A and skip the next instruction? So result of incrementation was in R1 and skip the next instruction. Suppose that is the next instruction is whatever is the next instruction, where exactly that was. In the fetch we have, in the fetch itself we have incremented this particular value and it was pointing to the next instruction. So that instruction need to be skipped, right? So PC was already pointing to the next instruction. So if R1 contains 0, then PC should be incremented by 1 more, so that the instruction which was there in PC right now is the next instruction to increment a instruction. That will be skipped. That is how the operations are being performed, right? That is how the the execution, the whole thing is performed. And remember one thing, if R1 equals to 0 is a if then else condition, that means even in control unit I require if then else. Alright? So that means the microprogram, wherever the microprograms are, they also need to check flags, and on that basis the required circuitry or required control signals will be activated, and that is how the instruction execution as far as related to a particular instruction using the micro operations will be performed. So there is a cohesion between between the control unit as well as the arithmetic unit and the memory as far as fetching the information from the memory and all these things. There has to be a lot of cohesion between the bus, between the ALU, between the register, all the registers, and between the control unit, because that is how the whole sequence of operations are going to be performed. Now moving on to the next statement, this is instruction pipeline. Now this is a very important concept, although it is not related to what we have been discussing so far. But instruction pipeline is something which primarily does a lot of work. I mean, it is something like enhancing the speed of the processor. If suppose all these sequences are to be performed in sequence, right? So first the instruction fetch will be done, then the indirect address will be done, then the execution of the instruction will be performed, and the storing of results will be performed. So if all these things are being performed, right, they can be performed in a sequence. Can they be performed in an overlapped fashion? Now that's a difficult question, right? And this is the basis of instruction pipeline. So if an instruction execution can be divided into several number of steps. First one is instruction fetch, You saw the 3 or 4 micro operations which can be performed in 3 steps only, right? Then instruction decode, so this is going to be performed within the processor. Then operand fetch, then execution, technical execution, and storing the result. So there can be 3 or 4 or 5 depending on the design of the machine. Actually the reason why I'm saying 2, 3, 4 or 5, because all these steps 1, 2, 3, 4 and 5 should be comparable. Then only instruction pipeline makes a sense in that particular sense. Why they should be comparable? Because all the segments, suppose an instruction is performing instruction fetch, the second instruction should also perform, like this block size should be same. The time taken for each of the operands should be the same. Then only the pipeline will proceed in the rightful manner, right? And second, they should not be dependent on each other. So that means if instruction fetch is there, it should not interfere with operand something, that is operand fetch, right? Because some instruction will be doing operand fetch along with it. So they should not be interfere with each other. So there should be different circuitry for that okay. So all these steps. So more complex is your processor if you are doing the instruction pipeline. If your processor is complex, it does not make, the point is that we want to make the instruction execution faster by doing the overlapping of instruction execution. There are more problems as far as instruction pipelines are concerned, in addition to the hardware which we have discussed so far. But look into the instruction pipeline so far. So if I just have these 7 instructions and there are 5 steps, 5 time slots. So in each, suppose I'm executing all these instructions in a sequential manner, then there will be 35 time slots which will be required to execute all these 7 instructions. But how many time slots are being required using this instruction pipeline? Only 11 slots. And how we are proceeding? Instruction fetch, instruction decode, like that. When the instruction decode of the first instruction is going on, at that point of time, second instruction will be fetched. It's like that. When these 2 operations are going on, the third instruction will be fetched. Okay, 4th instruction will be fetched here, 5th will be fetched here, 6th will be here, and 7th will be here, and the pipeline will be now full. So pipeline is full and the whole thing will go on very, very well. However, there are problems. Whenever you do a brilliant concept, there are problems with that particular brilliant concept. And in this particular brilliant concept is the if-else condition. Suppose this is an if condition and branch is to be taken to, let's say, instruction 7. That means execution of 4, 5, 6 is not required at all, right? And we will not come to know about the branch is to be taken or not till the execution is there, right? Till the execution EX is going to be there. That means we have to undo 4, 5, 6. We have to empty the pipeline and then start with instruction 7. So there is a branch penalty. All right. So branch penalty is always going to be when we are doing instruction pipeline. There are techniques of overcoming these branch penalties, right? It's not that everything has been left to the lurch, but those things, if you want to know, you need to go to the further reading and learn about it. All right. Second kind of problem is, suppose this instruction is evaluating an operand C, which is required in this particular second instruction. All right. C is being used here and C is required in this particular equation, second instruction. So there is a dependency of data. So that will not be available till the execution takes place. So once again, this particular instruction has to be delayed. So there are many problems in the instruction pipeline. I mean, there are no free bullets, no free things as far as the life goes and everywhere the things are, right? Similarly, in instruction pipeline, there is nothing free. All right. So this is how the whole instruction pipeline works. But overall, instruction pipeline does increase the efficiency of execution, and there are a lot of steps are taken to make it more efficient as far as instruction pipeline is concerned. Now, with this, we have dealt with a fair number of basics about the information, and that is instruction set, the micro operation. Let's now focus on ALU organization. And this is going to be once again, if you have understood the first two concepts, then only you will be able to make this particular thing off very, very easily. Now, this is a typical arithmetic operation or unit. And if you remember the full adder circuit which we had designed, and there were 4-bit adder we have created, right? Ripple 4-bit adder. It something looks like the same circuit, except we have added a multiplexer here. All right, and in the multiplexer there are two select lines which basically determines which of the, like C in is directly going to the adder. So full adder adds 3 bits, right? One of the operand is being fetched directly, but we are controlling the second operand. All right, and it is only a partial table which has been shown over here. You can refer to the full table as far as your block is concerned. Now, how exactly this thing is going to work? So, A is directly going to the full adder. What we are controlling is the B input. All right. So, what input will be going to from the multiplexer, I mean the Y input rather than saying B input, what is going to be Y? All right. X is going to be directly as A, right? So, the first operand is coming directly, C is coming directly. Okay, what is being controlled is B, and this is an arithmetic operation being performed. This is actually an arithmetic logic unit, one single bit of that. Okay. Now, if B is coming directly as 0, so select signals will be controlling whether 0 will be selected, 1 will be selected, 2 or 3. So, you will be basically S1 and S0 will be determining what is going to be selected. All right. So, S1, S0 is going to, so 0, with 0, if what we see, what is connected? B0, right? So, bit 0. So, similarly, all units which will be there in parallel, right? So, B1, B2, bit 1. So, the input is going to be the first bit of input B. It is fetching the first bit of input A. All right. So, A is always there with X and B0, right? So, B0, the bit 1 is directly coming here. So, if I have S1 as 0, S0 as 0, so there are two entries over here because C in can be 0 or 1. So, we will consider it as only one entry. All right. So, what is going to be Y value? Because there are multiple, so it is going to be B0 is directly coming to it, right? So, it is going to be equal to B, right? B0, B1, B2, B3 for different adder units, right? So, there can be more units, 1, 2, 3, 4 like that, and all will have the similar circuit. So, the for the adder units, what will be going in? Complete B. B consists of B0, B1, B2, B3 bits, right? So, B0 is coming here, B1 will be going to the next one, B2 will be going to the next, and so on and so forth. All right. So, if select input is 0, we get B as input. However, if select bit is 1, right? So, this is 0, 1, these two cases. What we are seeing, we are not considering in this particular diagram right now. So, what is going to be entering? B increment. Why? Because we are complementing B here, and that is going to 1. So, B complement will be going here. All right. So, simply B complement will be going into the input. No problem. So far, so good. All right. Okay. Now, next, what happens? Okay. Now, what happens next is the third. Over here, logic 0. So, we are connecting it to logic 0. So, if second input is connected, okay. So, what is the, once again ignore the scene, what we are getting? 1, 0, right? 1, 0 is 2. All right. So, in this particular case, what we are getting? 0 being fed. And in case logic 0's inversion, right? So, 3 is coming to that. That means for last case, all ones will be coming to the, all ones means 3, all ones will be coming, all zeros will be coming, all 1 bits will be coming to all the full adder units. Okay. So, this is how it is going to work in this particular case. Now, how it relates to the micro operation. Now, let us look into the micro operation of each one. Okay. So, if I am putting S01, so this is 1, 0, 0 and C in is 0. So, what is the input of X? Obviously, A, right? What is the input of Y? B for all the, for every full adder, this will have B0, this will have B1, and this is a full adder. So what is the result of this particular full adder? A plus B. So A is coming here, B is here. So A plus B is going to be the output, right? Carry bits, etc. can be adjusted. They are being passed on to the next one. But technically speaking, so when Cin is 0, what is going to be the operation? What is going to be the micro operation which is being simulated by this particular unit? Simply A plus B. That means register A, if I am putting register R1, right? R1 is inputting A0 and R2 is inputting B0, then it is simply addition of register R1 with register R2. And wherever suppose it is going to register another register the output, then we can simply say R2 gets R1 plus R2. So this is that particular simulation. Look into this. So what we are getting? Still we are inputting B, but there is a carry in. Alright. So what are we going to get? A plus B plus 1, right? A plus B plus 1, which is coming from Cin, right? So the operation is R1 plus R2 plus 1. Alright? What is this one? This is a very interesting one. Okay? 0, 1, 0. So what we are getting? That means B complement we are getting. So overall effect is A plus B complement, because input bit is 0. A plus B complement is subtraction. A minus B plus 1. So there is already a carry, right? So this is called subtraction with borrow, because we do subtraction with 2's complement, right? So 1 is missing over there. So this is subtraction with borrow. What about this one? Over here the 1 bit is already there. So this is simply A minus B. So this is a subtraction of micro operation which is being done. Alright. In this particular case, simply transfer. Okay. The output is going to be A, right? In both the cases, and this one is going to increment A by 1, right? So this is simply transfer A, this is increment A, alright? And this is, when we are inputting 0, this is actually decrementing the value, alright? This is going to be decrement, so you can test it. Suppose your value is 0, 1, 1, right? Just 3 bits. And I add 1, 1, 1 to it, right? So what I am going to get? There will be carry out 1 which is ignored. So we get 0, 1, 0 as output. So the carry out will be ignored. So you can try that particular thing out. This will actually decrement your value, register R1, alright? Or the value of A will be decremented by 1. And this is basically what is there? It is the 2's complement stuff, right? Because the input is all 1's plus 1, alright? It's no 2's complement, that is simply the 1 will be ignored, so nothing, just transfer. So like that all these micro operations can be simulated from this particular data, and they have been completely given. These are just 7 or 8 which I have shown to you, but and these are 8 only, and they are in your block also contain 8 only. There the description of all these operations is also given. So study them as per the description which we have today, right? You will be finding it easier to go through them, and you will understand them. Do it today itself, don't delay it, okay? Now the second thing which we have in the micro operation sequences is 8 out of 16 possible logical micro operation with 2 bit. Now this table is also from your block only. Now x0, suppose we have 2 bits, x and y, right? So these are the possible values, x0, y0, x0, y1, 1, 0, 1, 1. Now what are the possible outputs? Suppose x0, 0, what is the output? 0, 0, 0, 0. So what we are getting? Technically we are clearing that particular register. By doing this particular micro operation, if the output is all zeros, right, with these 2 bits, so I am simply clearing the information. Now is the output of 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. What is that operation? AND. So technically it is AND operation of x and y, right? So just by using 2 bits over here, we can simulate in fact 16 logic micro operations, and out of that we can select as many. Your block shows that we have selected only 4, which includes AND, OR, NOT and XOR. Alright. Over here what we see, x0 is 0, this is 0. Now this is what is there, 1, 1. When x is 1, that is the output. So F3 equals to x. The fourth output is, okay, when the truth table shows 0, 1, for this value 0, 0 it shows 0, for 0, 1 it shows 1, for 1, 0 it shows 0, and 1, 1 it shows 0. It is x prime y. That is why I have written x prime over there. So you can see x prime, alright. So where exactly, that is x prime y, where exactly you find 1, where x prime is 1 and y is 1, right. So this is why it is, x, this is for the different one. I showed you different one. This is for this case. So for this case you have x, y prime. So y prime is 1 here, x is 1 here, so that is why you get 1 here. For rest all cases you will get a 0. So like that you can interpret the truth table. So this is just representing the truth table for two binary variables x and y, and that is how, I mean, it can simulate 16 logic micro operations based on the truth table. All these micro operations are different from each other. XOR is an important one over here. You know about it, x0, y0, output is 0, right? x0, y1, y output is 1. x1 equals to 1, y equals to 0, this is what it is, and x1, 1, y1, for XOR it should be 0. So that is an XOR operation. So that's how the micro operations can be simulated, but only few can be selected, and accordingly circuit will be made for the logic micro operation. As far as shift operation is concerned, it is as simple as shift register. So you got to use the shift register, which can shift either into towards the left or to the right, and additional circuitry will be required if you want the shifting controls, right? So if you want shifting control, then additional circuitry will be required so that you can circulate, you can do whatever kind of stuff which is required as far as the stuff is concerned. So let us now try to conclude this particular whole bit of discussion. What I have tried to tell you today is that one of the most important things as far as CPU organization, or when we define CPU, the very first thing you should know is the instruction set. And one of the finest example of instruction set is 8086 microprocessor. So you can refer to 8086 microprocessor and what way the registers are, what way the different units are, right? So you can come to know about the CPU organization in that particular sense, and that is why we discussed it first, right? So instruction set is very, very important, and instruction set primarily include what? The operation code and addressing modes and operands, right? So operation code, addressing modes are basically used to interpret what operation is to be performed, and addressing mode tells us where exactly the operand is and how it is addressed, whether it is an address of operand or it is address of operand, that is indirect, that is how it is. But once we know about the instruction set of a computer, the next good thing to know about is how those instructions will be executed, right? And instructions are executed in a step-by-step manner. So those step-by-step, those are operations, are called micro operations, right? So instruction fetch will have 3 or 4 steps. Instruction decode, probably it is just control unit interpreting where exactly what kind of micro instructions. This micro instructions is in unit 4. So what kind of micro instructions, where exactly are those micro instructions for the given instructions are going to be. Okay, then moving from this, then the execution takes place step-by-step manner, and they all are determined by the micro operations. Now these micro operation, which micro operation is to be enabled? It is to the role of control unit, right? So control unit precisely knows. For example, if we are doing the fetch, right, instruction fetch, and suppose PC is to be incremented. Obviously, a set of control signal only is going to do this particular operation, which is going to issue the micro operation of incrementation, which we have shown you in the ALU, right. So, in the ALU, what how the S1, S0 and C in, right. So, those S1, S0, C in will be controlled by the control unit, and this particular, which circuitry is to be enabled, that is also to be controlled by the control unit, and those are the control signals. That is the job of control signals, and that is why you require control memory in a microprocessor, because if you are implementing controls through hardware, fine, but if you are implementing through microprogram, then you require programming approach to control unit and microprogrammed control unit in that particular sense, right. But the logic starts when you are dealing with the micro operations, and from micro operations then you move on to the ALU, how those micro operations has been made possible, right, within the ALU, how those things are done. In addition to that, you have transfer, right. So, transfer operation also require control signal, right. For example, if address is to be applied, right. So, control unit only tell the memory unit like this address is for us. So, therefore, if you want to learn about control unit, you should be learning about the first the micro operations and the arithmetic logic unit, how exactly it implements those micro operations. So, this insight is essential. In fact, it will give you, I feel a lot of pleasure in learning about it. I am really hopeful that you will also enjoy learning about them, because it is very interesting concept that how whole thing can be simulated in a computer system, and we know something which we should be knowing, because we are utilizing computer for our day-to-day working without even knowing what exactly it is doing, right. So, maybe tomorrow if you decide to be an Intel programmer, you should be knowing all these kinds of things. So, with this, I think the essence or the crux of the CPU and all related stuff is now I think I have tried to communicate to you. However, you are please you are free to ask as many questions on it. This is not, once again, the whole computer organization course is not very obvious, simple course. It requires logical understanding, and who else have better logic than you, right? So, you are the best person to learn about it in a great details. Let me assure you, this is going to help you tremendously if you, when you become the operating system designers, when you become the machine designers, when you become the compiler designers, and that's what you should be 5 years from now, maybe, right? Because we don't want you to be sitting just doing application program all the time. You are doing professional course, and when you are doing professional course, your knowledge should keep on increasing day by day, and you should, you should be learning even after you complete your MCA. You should be learning in that particular spirit and going ahead into your career all the time. So, with this, I would like to end the session for the day. I wish you a lot of luck. If time permits, I'll take another session next week, completely giving you a complete roundup from the very beginning till the end of this particular course. However, you're most welcome to ask questions, as many questions as you like. Thank you for being with me. Bye for now.